Hi guys, I'm Eric and today we'll be continuing to learn number theory, and today we'll be talking about divisibility. Now you guys probably know what it means when we say A is divisible by B. When we say that A is divisible by B, we mean that there is a positive integer called, we are gonna call it K, which satisfies A equals KB. And we express this using a stick. And as we do with not equal, if we add this horizontal line onto the stick, we means that M cannot be M is not divisible by N. And if we just leave the stick alone, we mean that M is divisible by N. Yes, M is divisible by N. I always get confused, like, when do you say M is divisible by N or N is divisible by M? Now, GCD, well, we're going to start with common factor, or common divisor, or whatever you want to call it, as long as you're happy. Common factor, we're going to call it common factor, because that's what I'm used to. Common factor of A and B, let's say it's X. Then there are two positive integers called M and N, which satisfies A equals MX and B equals NX. And the greatest common factor, in this case the greatest common divisor, is basically the greatest of all x's. X1, X2, all the way to X, and pick the greatest. Now if the GCD of A and B is 1, then it means that they're relatively prime. Now, do not think that relatively prime means that they are both primes. It basically means that they have no common factor except 1. So for example, 4 and 9. Neither 4 nor 9 are primes, but then we see that 4 only have 1, 2, 4, 9, same only have 1, 3, 9, and except 1, there are no more common factors. So 4 and 9 are relatively prime, even though they're both not primes. Now we have gone into the basic definitions. Now we go into the practice area, and we're going to solve for GCD of 225 and 120. Now, you guys probably noticed that, look, 5 and a 0, well, one of their common factors at least is a 5. Now, it might not be the greatest, so we're going to use a prime factorization. So 225 divisible by 5, we get 45. Divisible by 5, 9. 9 is 3 squared. So 225 equals 3 squared times 5 squared. 120 divisible by 2, 60. Divisible by 2, 30. Oh my gosh. Divisible by 2, 15. Divisible by 3, 5. So 120 equals 2 to the third power times 3 times 5. Now we have 3 times 5 on both sides. So their GCD is not 5, but 15. Now this is kind of slow, and it will be very hard when we get like millions or billions or even trillions. So there's something called Euclidean, I think that's what you call it. Oh no, it's Euclidean. Oh my gosh, I get confused between Euclid and Euler. So Euclidean algorithm, we're going to start simple. This is not very simple, but it will be our starting point. And basically what you want to do is you leave 225 on the left side, and you try to get a number out of 120 that is closest, but not bigger than 225. And in this case, it is 1 times 120. The remainder is 105. Now, we leave 120 on the left side, then we do the same thing with 105. And it is 1 times 105 plus 15. And we find that 7 times 15 is exactly equal to 105. So the GCD of them is 15. It's pretty quick, huh? And even super big numbers, these thousands, it's already very incredibly hard to use prime factorization of these numbers. But Euclidean algorithm solves the problem just fine. So we see that it's 2 times 2809 plus plus 1113, and you can calculate this if you want. And we leave 2809 on the left side. We get 2 times 1113 plus 586. Yes, 586. And 1113 is equal to 1 times 586 plus 500 and wait a second, it's not 586. It's supposed to be 583. Well, 583 equals, no, I got messed up. 1113 equals 1 times 583 plus 530, and 583 equals 1 times 530 plus 53. Now we can see that 530, 530 is basically 10 times 53. So their greatest common divisor is 53. And it's much easier than doing prime factorization for both. And we summarize the Euclidean algorithm to look like this. Now you can pause the video and get a close look at it, but we're going to skip right to the proof. Now, in order to prove that it works, we have to say that Rn is equal to GCD of A and B. And we're going to let G be the greatest common divisor of A and B, which in this case, A is greater or equal to, it's greater or equal to B. Now you can also say that B is greater than equal to 1 of your liking, of your choosing, but it just makes matters easier to deal with. So we're going to look back at this Euclidean algorithm and we find that there's a plus 0. Well, we'll definitely be able to ignore that plus 0. So Rn minus 1 equals Qn plus 1 times Rn. So Rn minus 1 is divisible by Rn. Now let's check Rn minus 2. It is then Qn, and we already know what Rn minus 1 equals. It's Qn plus 1 Rn and plus Rn, common factor of Rn. So Rn minus 2 is also divisible by Rn. And if we continue to find if Rn minus 3 is divisible by Rn, we'll find that Rn can of these numbers, including A and B, is divisible by Rn. Now, this including A and B is especially important since it's the GCD of A and B. So we get that Rn is smaller or equal to G, since it is a common divisor and G is the greatest. So it must be smaller or equal. And then we're going to change colors. Then we look back at the definition of G and we find that there are two positive integers with m and n, which satisfies these two equations. Now we figure out if if we move this part to the left side, we'll get R1 equals A minus Q1B. And we're going to substitute A and B. So R1 equals mg times Q1ng. There's common factor of g, so R1 is also divisible by and we find that R1 is divisible by G, and you guys know what we're going to do next. We find that R1, R2, R3, all the way to Rn, these remainders are all divisible by G, which means that G must be smaller or equal to Rn, since Rn is divisible by G, and G cannot be greater than Rn, even though they can be equal. And we had also proved that Rn is smaller or equal to G, which means that G is greater or equal to Rn. So they both exist, don't they? So we find finally that Rn is equal to G, and we had proven that the Euclidean algorithm works. Rn is our final project. GCD is what we're trying to find, and they're equal. So EA works. EA is just the Euclidean algorithm. And that is all for today. See you next time.